Right, another example. Um, this one is about a rectangle, still on related rates. So, a rectangle maintains a constant area of 300 centimeters square, even though its length and width are changing. Suppose that the length is increasing at a rate of 6 centimeters per second. So the beautiful thing about this question that I love is I say that the area of the rectangle, regardless of what is happening, it's still going to be 300 centimeters square. So it is a constant. It is never going to change, regardless of what we do. However, we're changing the length and the width. So that's the first part of the question before the comma here. The second part say that even though its length and width are changing, just as I said, even though the length are changing and the width are changing, the area remain constant. So now suppose that the length is increasing at a rate of 6 centimeters per second. Basically what we're saying is that the length of this beautiful rectangle that we have is increasing at a rate. So the length is increasing at a rate of 6 centimeters per second. So every second we're changing the rate, we are changing the length of the rectangle. So this, when I think about this sentence, what it says that the length is increasing at a particular rate, what comes to my mind is the slope of the slope. So the length is increasing at a rate of 6 centimeters per second means that the length, so the dl dt, which is the same as l prime, is equal to 6 centimeters per second. So the reason why we put dl dt is because the length is changing. So the l is changing with respect to time. So they say that every second we're changing our length by 6 centimeters. So this is what it means. This is what it means. So we have dl dt, which is the same as l prime that many people will use, is equal to 6 centimeters per second. With this, I'm going to keep it this way. I'm going to keep it here in the box. And I'm going to try to find out what my first question is asking me. They're saying that find the rate at which the width is changing at a moment when the width is 15 centimeters. So they want me to find what is the change of the width. So we know that the length is changing, and this is the rate at which it's changing. So they want us to find what is dw dt, which is the same as w prime. So they want us to find what is this value when the width of this rectangle is equal to, let me read again, it says it's 15. So when I hear this, I want to figure out a way to solve this. So the way I will approach this is first to identify what is the relationship between the length and the width. So the relationship between the length and the width, we can either use the perimeter or we can use the area. However, if we go back to our first equation, our first sentence, they say that the rectangle maintains a constant area of 300 centimeters squared. So what that means to me is that we have the condition are set so that we use the area of this rectangle. So from my geometry knowledge, I know that the area of a rectangle is equal to the length times the width. So in this case, if I want to find what dl dt is, I need to find the derivative of this whole equation. Why? Because we are considering L and W in this case as being functions of time, because they're both changing because of time. And the area is a constant, so it's also changing because of time in this case, because all of them are functions of time. So in this case, I have to find d of this whole thing. With respect to t. I need to find d of this whole thing with respect to t. Now, when I do find what this is, what's going to happen is that I will distribute this like this. So I have dA dt is equal to, how do I differentiate this? I use it as a function. So remember that we're saying that L is the same as f of t and W is the same as g of t. So how do I differentiate this? I'm going to use the product rule because I am having a function multiplied by a function. So I'm going to use the product rule. What does the product rule say? I have to do f prime of t multiplied by g of t plus g prime of t multiplied by f of t. So with this, I knew that my f of t was L and my g of t was W. So I can substitute it here by saying that f prime of t would be L prime multiplied by g of t, which is W, plus g prime of t, which is W prime, multiplied by f of t, which is L. So in this case, my dA over dt, is equal to the derivative of the length times the width plus the derivative of the width times the length, right? So if I try to find this, I know that from the first iteration for the first set of instruction, the area is always going to be 300 centimeters squared, which means that no matter what I do, this A is always going to be 300. And if I have a constant, 300, and I find the derivative of this constant with respect to time, this will become 0. Because the derivative of a constant will give me 0. So here, what happened is that I have 0 is equal to L prime W plus W prime L. Okay. What are we trying to find again? We're trying to find W prime. We're trying to find this one here. And I know that L prime, this one, is equal to 6 centimeters per second. And I know that I need to find this W prime when the width here, when my width is equal to 15 centimeters. So I can just put that back in, 15 centimeters. Now I need to find W prime, but I don't know what L is. So, we have a problem. We need to figure out what L is. But I can do that very easily by going back again to what my first instruction was. This area is always going to be the same. So the relationship between the area, the length, and the width is this one. So if I'm trying to find what is W prime when my width is 15, I can immediately say, because the area is always going to be constant, I can just find what is going to be my length when the area is 300 and the width is 15. So now I have an equation. I know that at 15, my area is still, when my width is 15, my area is still going to be 300. So I will try to solve for L. I'm trying to find what is the length at that exact moment. So I have this set of equation that I will divide both sides by 15. So I end up with 20 is equal to L. So my length when my width is 15 is equal to 30. With this information, I can come back and take this 20 that I just found for the length, and substitute it back here. So what I have is 0 is equal to 6. I'm just going to drop those units for now. So 6 times 15 plus W prime, which is what we're trying to find, plus W prime times the length, which is, in this case, the length, which we just found to be 20. So I have 6 times 15. I'm going to use my calculator for that. I'm not a machine. 6 times 15 would be 90. And then plus, of course, 20 W prime. So now I want to solve for W prime. So I will bring this one on this side. So I end up with negative 90 is equal to 20 W prime If I divide both sides by 20, I end up with negative 9 over 2 centimeters per second. So this tells me that when my width is 15 centimeters, the change of the width, the rate of change of the width is actually negative 9 over 2 centimeters per second. Okay, that was the first one. So now we want to find B. What does B tell us? B tells us to find the rate at which the perimeter is changing at the same moment. Wow. We had the area. Now we want to find the perimeter. So what is the formula to find the perimeter of a rectangle? So I'm going to do B on this side. So B, the area, the perimeter of a rectangle is equal to 2 length plus 2 width. Perfect. So I want to find what is the perimeter. So I can just take the derivative, I want to try to find the rate at which the perimeter is changing at the same moment. So I can take dp over dt and then d of 2l plus 2w over dt, because both of them are always changing with respect to time. So this, remember that w and l are functions of time. So I end up with dp over dt is equal to 2 times L prime, which is the same as, I'm going to be consistent here and put dl over dt, plus 2 times dw over dt. This is the same as L prime, and this is the same as W prime. So what happened now, I remember that I know what my DL was, and we just found what dW is. So dW was this value here, and my DL was 6. So I can come back here and say that dP dt is the same as 2 times 6 plus 2 times negative 9 over 2. So when I do this, gives me 12. This would give me negative 9. So dP dt is equal to 3. So we just found out the rate of change of the perimeter when our width is 15, therefore the length is also 20. So now, C. This is a quite complicated one, but it's doable. So they want us to find the rate at which the length of the diagonal is changing at the same rate. So let's imagine we have a rectangle. Not the perfect one, but still, oh, okay, perfect rectangle, I think. Let's imagine we have a rectangle. So we'll ask to find what is this, the diagonal. So this line that cuts the rectangle into two different triangles. Remember that this here will be the width, the smallest side will be the width, and this will be the length. So what is the formula that I can use to relate this, and this side? When I see this, that reminds me of a triangle, a right with this 90-degree angle. When I see this, this reminds me that I can use Pythagorean theorem, which says that the longest side of a right angle triangle is, let's say, I'm going to call it C. So tell me that if I want to find it, it will be C squared plus A squared plus B squared, right? A squared plus B squared is equal to C squared. So this long side here that I just named C is the same as taking C squared plus C squared, is equal to the length squared plus the width squared. So if I want to find what is the value of C, C would be the square root of the length squared plus the width squared. Oh, we just found a formula that linked this diagonal line, this one here, with the width and the length. Perfect. So now, because all of them are functions of time, I need to find how they're changing. We want to find, as the question is asking us, find the rate at which the length of the diagonal is changing. Once again, we're trying to find the rate of change of c in this case. So I can take the whole derivative, the derivative of every single one of them, because of function of time. So I can take dc over dt is equal to d of this whole thing here plus wt or w over dt. So dc over dt is dc over dt, of course. This is what we're trying to find. On the other side, if I try to take the derivative of this one, I would have to use the chain rule, right? Chain rule, because I have two functions actually inside of this giant function, because square root of something is actually a function. So what I can do is I can rewrite this as L squared plus W squared, okay, to the power of 1/2. Here first I can use the power rule, of course I'm going to use the chain rule. So I can drop this one down. So I have 1/2 multiplied by L squared plus W squared. So I have 1 minus this one, minus 1, of course, as we know it. So it's going to be times negative 1/2 multiplied by the derivative of what is inside here. So multiply by the derivative of the inside, that would be 2w prime plus 2, okay, sorry. This would be, so this would be 2, so let me see, this would be 2 L prime plus 2 W prime. Perfect. Yeah, that's it, because I can take L is equal to f of x. So if I take f of x to the power of 2, and I need to find the derivative of what is of this, that would be 2 times f of x times f prime of x, because this is a function. Implicit differentiation at its finest. So what happens next? I have this whole thing that looks like a mess. This whole thing would give me this. So what I end up having is this giant, long, and perhaps confusing equation, which I'm just going to rewrite it like this: 1/2 square roots of L squared plus W squared multiplied by 2 L prime plus 2 W prime. This is the same as dW dt, and this is the same as dl dt, for those of you who like to use that notation. So this is long, but we're almost there. So dc over dt is equal to this whole thing. But now remember that I said to find the rate at which the length of the diagonal is changing at the same moment. Remember that we already found all of those values. We know what the length is at that moment. We found that it was 20. We know that the width is 15. And we know that, once again, the length is 20. The width is 15. And we know that dl dt, which we just found, which we knew from the beginning, was 6 centimeters. So 6, and W dt, which we just found to be negative 9 over 2. I can put all of them in here, right? So what I end up having is 1 over 2 times the square root of 20 squared plus 15 squared times 2 times 20 times 6 plus 2 times 15 times negative 9 over 2. Okay, this is a giant mess, but it's doable. So this would give me, so 20 times 20 would give me 400 plus 15 times 15. What did I give me? Using calculator here, give me 225. So 225 plus 400, that would give me 625. So I have 1, so I end up with, 1 over 2 square root of 625 multiplied by, this one would give me 60 times 20 times 2, 60 times, 6 times 20 times 2, that will give me 240. So this is 240 plus, so this I can already simplify those two so that it's easier for me to use it in the calculator. So I end up with 15 times negative 9, which will give me negative 135. So this here, 240 minus 135 would be 105. Perfect. So I end up with this giant thing, 1 over 2 times square root of 2 of 625. This whole thing times 105. The square root of 625 is 25. So I end up with 1 over 2 times 25 times 105. So I end up with 1 over 50 times 105, which is 105 over 50. And you can simplify that. 105 over 50 is the same as 21 over 10, which is, in decimal form, 2.1 centimeters per second. So this is the rate at which the diagonal line is changing at the same moment that all of this is happening. So I hope you enjoyed. I hope it was useful. Let me know if you need any help or if something is not making sense and I can try to explain.